In this video, we take a look at the t-distribution, another commonly used bell-shaped distribution for quantitative data. So we use the t-distribution for quantitative data analysis when we don't know the population standard deviation. So let's read a bit about the t-distribution. In all of our previous examples, we have known the population standard deviation, sigma. When we know the value of sigma, we are able to base confidence intervals and hypothesis tests for the mean mu on the z statistic. In reality, costs and other technical problems typically preclude a researcher from sampling an entire population and calculating the standard deviation for the whole population sigma and the mean for the whole population mu. Therefore, the researcher must somehow estimate the sampling distribution and standard error without surveying all members of the population. Fortunately, statistical research shows that when certain assumptions are met, the sampling distribution can be estimated. The shape of the sampling distribution for this type of problem is different from the normal distribution, especially when the sample size is less than 30 subjects. This sampling distribution is given the special label of the t-distribution. So this name, the t-distribution, is what we use in English language statistics books. And it's named after this paper written by William Seeley Gossett, the man whose picture is at right, and he published under the pseudonym Student or Student T. He worked at the Guinness Brewery in Dublin. He published his paper in 1908, and he was interested in the problems of small samples, for example, the chemical properties of barley, where the sample sizes might be as few as 3. So there's different stories of why he published under the pseudonym. One is that the Guinness factory preferred people to use pen names. One is that he did so that competing breweries wouldn't know that it was Guinness using the t-tests. So different theories as to why he published this paper under Student T, but that's how the t-distribution got its name. For practical purposes, the shape of the t-distribution is identical to the normal distribution when the sample size is large. However, when the sample sizes are small, below 30 subjects, the shape of the t-distribution is flatter than that of the normal distribution, and the t-distribution has greater area under the tails. The reason that the distribution is not normal is because the standard error is estimated using the sample standard deviation instead of the population standard deviation, and that's because the population standard deviation is not known. This creates some uncertainty that is reflected in the t-distribution having greater area under the tails than the normal distribution, especially when the sample size is below 30 subjects. So you can sort of think about it, when we've got a small sample, we're leaving more room in the tails, more room for error because we're less certain because we're using just sample data. There might be some outlier that's not included in our sample data, some very tall or very short person if we're thinking about heights, or somebody with more extreme values that didn't get captured in the sample data. As you can see, even when the sample size is 15 subjects, it's hard to tell the two distributions apart with the naked eye. So we've got the normal distribution on the left here, and the t-distribution. This is when we have 15 subjects. So they look almost the same, but we can see from the shaded area that there is 7.4% in the tails of the t-distribution area over here. So even though we can't tell the differences apart with the naked eye, we say nonetheless the differences may be important when comparing the area under each curve at the same standard score, meaning the same z-score or t-score, away from the mean. So if you are calculating the t-score by hand, you'll need to consult with a t-distribution table showing the area under the tails, or the proportion corresponding with the t-score. This is similar to using the normal distribution table to find the area under the tails corresponding with the z-score. So if we were taking our class 20 years ago, you'd have two sets of tables, one for the normal distribution and one for the t-distribution. The values in the table are slightly rounded, so these results from the table are approximations. So we are going to use StatCrunch. So in StatCrunch, when we do the t-test, we have two choices. If you're working with a data file, you'd have your data in two separate columns. And then you choose stat, t-stats, one sample or two sample with data. And then if you already have your summary data, you choose stat, t-stats, one or two samples with summary. So let's look at an example comparing the normal distribution and the t-distribution. So we're going to head into StatCrunch, go to Stat Calculators, and open up a normal calculator and a t-calculator side by side. The settings are going to look like the screen below. Over here on the right, you see the t-distribution has df, which stands for degrees of freedom. The number of degrees of freedom is one less than the sample size, n-1. The concept behind the n-1 calculation. If you know all but one of the values in a list of size n, and you know the total of the values, you can work backwards and figure out the missing value. So to figure out all the values in a list of length n, you only need to know n-1 of the values. Scientists name these n-1 values the free components. So we are going to head into the calculator, and in the t calculator, we're going to adjust the degrees of freedom to be 15, then 20, then 30, and then 50, and finally 75, and go see what's happening to the shape of the t-distribution. So we're going to head into StatCrunch. We're going to open a blank StatCrunch, and we're going to pull up both of these calculators. So we'll go to Stat Calculators Normal. We'll put that one over on the left. And then we'll go to Stat Calculators T, it's just the letter T down here. And let's get them so that they're both about the same shape. So they both are centered at 0, and we can see at 10 degrees of freedom, the T calculator looks a lot narrower. So let's go up to 15 degrees of freedom, getting wider, and then we're going to go to 20 degrees of freedom. We see the T calculator getting a little bit wider, and then let's go to 30, looking more and more like the normal distribution, then 50, then 75, and we see as we increase the degrees of freedom, that means the sample size is getting bigger. The T calculator shape gets closer and closer to the normal calculator. So that's what we explain here in part A. As the degrees of freedom, what we call df for short, increase, the shape of the t-distribution gets wider and closer to the normal distribution. Now we're going to do the comparison by changing the probability calculation on both distributions to be the probability that our x value is less than or equal to -1. And then we're going to adjust the degrees of freedom again from 15 up to 75 and see what's happening to the areas as we go. All right, so we are going to set these both to have our x value less than -1. All right, so in the normal distribution calculator, we're not surprised to see the area is right around 16% or 0.16. It is 0.1587 if we round it. Over here in the t calculator, it's a little bit above that. It's 0.160263, so very close. Oh, and that's because we're at 75 degrees of freedom. If we start at 15 degrees of freedom, we see we're a little bit further above 16% at 0.1666 if we round it. So then notice as we go up to 20 degrees of freedom and then 30 degrees of freedom, our area here is getting closer and closer to 0.16. So if we go to 50, we're at 0.1610, and then 75, 0.160263. Let's go to like 200 degrees of freedom. So that'd be if we had 201 data points. See how now we're at 0.1593 if we round, getting closer to the normal distribution. Let's say we had 1,000 data points, so we have 999 degrees of freedom. Now we're really, really close to that 0.1587 that we see in the normal calculator. So our explanation here is that as the degrees of freedom, df for short, increase, the area in the t-distribution gets closer to the area in the normal distribution. So the bigger the sample, the closer the t-distribution is to the normal distribution. So in short, if you've got a small sample, you're going to want to make sure you're using the t-distribution because you know it might be different from the normal sample. If you had a sample of 1,000 people and you accidentally used the normal distribution instead of the t-distribution when you didn't know the population standard deviation, you would just had sample data, your results are going to be really close to the normal distribution. So for small samples, we want to be sure that we're using the t-distribution. For large samples, if you make a mistake, it's not going to have too much of an impact on the calculation.